Hey guys, hope everybody's doing okay. What we're going to do today is continue with our first law of thermodynamics, which focuses primarily on enthalpy, or heat, or energy. And we're going to see how that applies to an overall chemical equation or a combination of chemical equations to give us a chemical equation that we're looking for. So we're going to start out by deriving enthalpy a little bit, and there's not a lot on this slide here that we need to be able to reproduce or memorize or worry about too much. But on your note sheet somewhere, it should say what the definition of enthalpy is. And the enthalpy is H in this case here. So it's the internal energy of your system. That's what E is, plus the pressure and volume, the product of the pressure and volume acting on that system. Okay? You may or may not have watched an introductory lesson on work or this pressure and volume product here. And if you didn't, it's okay. I may have cut it out depending on what school year this is. But that's our formal definition here of enthalpy and the equation we would use to find enthalpy. If I do some different substitutions for the internal energy of our system, you can see how I kind of progress through it here. I'm just doing some different substitutions for some of these variables. And what we end up with overall is a simplified version of this equation, basically. All right? The simplified version of this equation, which is enthalpy equals internal energy of a system plus the product of pressure times volume, is what we end up with right here. Okay? So at a constant pressure, the change in enthalpy, okay, is equal to Q, which is heat, right? Which we talked about when we did our calorimetry, Q equals MC delta T type problems, and that whole concept which came before this one. So the idea here is that we never truly know the internal energy of a system, but we could always find the change in energy of a system. So that's why typically we're going to find something called a delta H, or a change in energy, and not a true energy or enthalpy value. Okay? So the bottom line here is that if there's no change in volume of a gas at constant pressure, we have a change in energy is equal to our change in enthalpy, which is equal to Q, which is heat. So that's why when I go through a lot of these problems, I use energy, enthalpy, and heat all interchangeably. Okay? So depending on, and just how I'm going through the lesson or the content, I could say energy, enthalpy, or heat. You could basically know that they all mean the same thing, basically. All right, so that's how we define, or that's how we get our delta H here, and that's how we know what those terms, represent. And let's take a look at it in terms of a chemical equation. Okay, so enthalpy is something called a state function, and state functions aren't too difficult to think about here. It's no matter what pathway we take, the change in enthalpy will be the same. You want to think of this as like displacement. All right. So you want to imagine here that we're going on a road trip. All right. And our starting point on the road trip is here in York, Pennsylvania. Right. And we want to go on a road trip to a very magical place. All right. And that magical place we're going on our road trip to is, of course, Disney World in Florida, right? So there are multiple different ways we can go on our road trip from York to Disney World. We could take a more direct route, right? Take some of the main highways south, and we can get to Walt Disney World pretty easily, right? It might take us a little bit of time, but we can go in a relatively straight line and get to Disney World. Another way we can go to Disney World, though, is to take the scenic route. Okay, so our pathway might look something like this. Okay, either way, where do we end up? Well, we end up at Disney World, right? Did the distance between York, Pennsylvania and Disney World change depending on what pathway we took? Well, the answer is no. The distance between York and Disney World is X number of miles, right? That didn't change. That's consistent. Now, we could expend different amounts of energy getting there, right? But the overall displacement is the same, all right? So basically what I'm trying to point out to you here is with enthalpy, or energy, you can get to an overall chemical equation. Okay, there might be a couple pathways, a couple reaction pathways to get there, but the overall change in enthalpy or energy will be the same no matter what pathway you take. All right, let's take a look at an example. Here's a basic chemical equation. We have carbon plus oxygen produces carbon dioxide. Now sometimes, and we'll get into this when we do our next unit on kinetics, you don't always just have a carbon and an oxygen combining to make CO2 in one shot, right? Sometimes you have to go through like maybe 2 or 3 chemical reactions to get to where you want to go. So here's an example of that. So this reaction pathway is when we're taking carbon plus oxygen and we're producing carbon monoxide and an oxygen atom, okay? We're going to get into like intermediates and catalysts and things like that in the next unit on kinetics. So this monatomic oxygen looks really weird here, but just know that this would be like a really quick, like unstable part of the reaction. And then we would obviously move on to the second reaction here to take our carbon monoxide plus our monatomic oxygen to create CO2. All right. So if you look at what's happening here is we have carbon plus oxygen ultimately producing CO2, but it's in the form of a two-step process. All right. So I'm going to show you how to cancel a few things out here, which is important. We're going to end up doing this in the next couple minutes. I think it's pretty easy. The products of this first reaction, carbon monoxide and that monatomic oxygen, are the reactants in the next equation. So if I'm going through and like adding up these two equations, my reactants on the second equation, CO and O, cancel out with the products of that first equation, right? So your product of the first equation becomes a reactant in the second equation, and you ultimately end up at your final product, which is CO2. If you look at the overall equation then, after we looked at what we canceled out, we have C plus O2 yields CO2. That first reaction took 75 maybe kilojoules of energy per mole, something like that. I don't have the units on here right now. They're not important for this particular part of the lesson that I'm on. The second reaction took 25 units of energy. All right. So the overall process, if you add up reaction 1 plus reaction 2, is going to give us a net delta H of 100. Let's take a look at another reaction pathway though. So if I have something like this where I have C plus O2 plus platinum produces C plus some platinum oxygen formation here. And then I look at my second equation, and I have carbon plus that platinum oxygen item producing CO2. Let's do what I did in the last equation. Carbon is a product here and a reactant here, it cancels. This weird platinum oxygen thing is here and here, so that cancels. And it looks like here platinum is really just acting as a catalyst. This really probably should have been above the arrow here. So you see it doesn't cancel out. So that would be above the yield sign if this was written a little bit differently. So don't worry about that right now. That's a catalyst. We'll find out later that catalysts, we know that they're not used up in a chemical reaction. You can reuse them over and over again. So you're not going to write them in your overall reaction at the very end. So what you're left with here is, again, C plus O2 yields CO2. Look what you have. First reaction takes 35 units of energy. Second reaction takes 65. Overall, delta H, or enthalpy of this chemical reaction process, this system of equations here, is going to be 100 units of energy. Notice how we have two different reaction pathways, both giving you the same delta H. That is why enthalpy is a state function. So if we're starting with carbon and oxygen, no matter no matter what pathway we take to get to our product, the overall change in enthalpy will remain consistent. Okay? Just like no matter how we get to Disney World, the distance between Disney World and York is not changing. All right? So what we can do is look at a system of equations and reorganize them a little bit to figure out what your delta H value, your enthalpy value, would be for an overall equation. That's called Hess's law. There are a couple different layers to Hess's law. This is the first part of the Hess's law lesson. And And there are other different shortcuts and things we can take along the way. But Hess's law says if a reaction is carried out in a number of steps, the change in enthalpy, which is delta H, for the overall reaction is the sum of the change in enthalpy for each individual step. I really like doing these problems. I try to think of it as a puzzle I'm trying to solve, and a lot of students tend to do really well with this, and they kind of agree with the whole puzzle analogy here for how these have to work. So look at the example on the screen. It should match up with the, actually this one's not in your note sheet, so that's okay. Look at the process then for how we do this. I have two reactions here. I have that first one with CH4 plus 2O2 yields CO2 and 2H2O. My change in energy there is negative 802 kilojoules. And my second equation is 2H2O gas yields 2H2O liquid. And that process gives me a change in enthalpy of negative 88 kilojoules. If you look at what cancels out here, we want to be careful. We have 2H2O gas here. That's a product of one reaction. It's a reactant in another one. So those cancel out. What do you have left? You have CH4. Let's bring it down here. We have 2O2. Bring that down. We have CO2 on the product side. Bring that down. And we have a product here. Bring that down. So you can see that the first equation plus the second equation, where we cancel out the like terms on the reactant and product side, gives us an overall delta H value of negative 890 kilojoules, because we have negative 802 from the first reaction, negative 88 from the second reaction. And again, it says the overall reaction delta H is a sum of the delta H values of each individual step. Gets a little bit more complicated though for something like this. So let's find the overall heat of reaction, or the change in enthalpy, for the equation that's highlighted in yellow. Now this one is on our note sheet that we could figure out, so I'll try to do this one with you to start out here. Look at the two equations that were given. First equation has 2SO2 plus O2 yields 2SO3, and the second equation is 2S plus 3O2 yields 2SO3. It's a little tricky at first to get these started, but once you get the hang of it, you try to find some patterns. You have a strategy that you know how to follow, and a lot of it tends to work out relatively well. So look at the overall equation you have. What I tried to do here is I try to find something in my overall equation and see where it is in the series of equations above it. All right. So the first thing that sticks out to me here is solid sulfur. I want to see where that is in my system of equations. If it's only in one place, that's good, right? Because I can kind of isolate where it is and see if it's in the right place. So I find it here, okay? And I don't see it anywhere else. So solid sulfur is in that second equation in my reaction mechanism here. But the problem is I need a coefficient of 1 in front of sulfur. And the coefficient in front of sulfur in the second equation here is a 2. So it's not good. So it's on the correct side. Okay, it's on the reactant side in the highlighted equation. It's on the reactant side in equation number 2 here. But it's too big. So what I need to do is multiply this whole second equation, including the delta H value, by 1/2. Okay, that's going to give me the coefficient in front of sulfur that I need. So let me write that underneath here. I'm going to try to keep it like I'm going to write it where the second equation would be. So I'll leave some space for the first equation above it because we haven't looked at that one yet. So I'm going to multiply my second equation by 1/2. And what I'll end up with is sulfur solid plus, now 3 times 1/2 is 3/2, or 1.5, O2 gas yields, if I take 2SO3, multiply it by 1/2, it gives me SO3 gas. And my delta H multiplied by 1/2 is going to give me, that would be negative 790 times 1/2, which is negative 395 kilojoules. Okay, keep in mind, I want to get to this highlighted yellow equation here. So my sulfur solid is good, right? I really don't want to touch my second equation anymore, right? Let's see if I can do something to the first equation to get what I want to cancel out to get that yellow highlighted equation. If I look at my second equation, well, actually, let's take a look at the highlighted one real quick. Look at your product. It's SO2 gas. Look at the product right here for the reaction we just wrote. It's SO3 gas. Well, I don't see SO3 anywhere in this yellow highlighted equation, so I need to get rid of it somehow. I need to have that cancel out somehow. I definitely can't have it as a product. So, I mean, I can't just get rid of it in the equation, in that second equation. What I need to do is manipulate my first equation here to get that SO3 to cancel out. So it's right here. Okay, it's a product of my first equation. It's also a product of my second equation. And since I don't want to mess with my second equation right now, because I already have my sulfur, I know it needs to be in that spot, I need to take my first equation and actually flip it. Okay, so let me write that. Okay, let me write that out. And actually, before I do that, if I flip it, my 2SO3 will be on the reactant side. Okay, so it'll be here. Okay, but if you look, I have a 2 in front of it and only a 1 in front of the SO3 right here. Okay, so what I need to do is not only flip my first equation, but multiply that by 1/2 as well. Okay, so what I need to do then, before I rewrite it for you, is we need to flip it. So that is actually going to take the inverse of your delta H value. So you're multiplying by -1. Okay, so if you just flip the reactants and products, you multiply by -1. And then I want to cut it in half. So what I'm ultimately doing here is multiplying by -1/2 for that equation. So let's go ahead and do that. So I'm going to flip the equation and multiply by 1/2. So my SO3 becomes a reactant. I cut the 2 in half to make it a 1. And that looks like it's the only reactant I have then. So I'll just leave this awkward space here. My 2SO2 gas will be a product. I also cut it in half to make it SO2 gas, plus my oxygen is now a product, and I cut it in half, so it's 1/2 O2 gas. That's just how I did it here. Like, you could look at this and say, wait a second, I know I need SO2 gas as a product, and the only place I see SO2 gas is right here on the reactant side of my first equation. So I know I need to flip it, right? And you need 1 SO2 in your highlighted reaction, and I have 2 SO2 in the first equation. So of course I need to cut it in half as well. So you could have noticed that first. Like, there's a bunch of ways to go through it, but that's the general idea for what you want to do. So your delta H, running out of room here, so your delta H has to be multiplied by -1/2. So -196 times -1/2 gives you 98 kilojoules. Let's make sure everything works out here. Okay, so my SO3 is here and here, so that cancels. And my oxygen, I need to do something with that. I only want 1 mole of oxygen for my overall highlighted reaction here. So I have 1.5 oxygens here and 1/2 here. So that'll cancel. And that 1.5 just becomes 1. Okay, so let's bring everything down. My only reactants then are sulfur solid plus oxygen gas yields sulfur dioxide gas, and my delta H for that reaction is 98 plus -395, which is going to give you -297 kilojoules. Okay, so that's my overall enthalpy change for this series of equations. Now, they're not all going to take you that long. At first, they will, okay, because you got to think them through. But then eventually you get the hang of it, and it kind of works out. Okay, give this one a try. I'll help you through it a little bit, and then we'll try one more, and that'll be it for today's lesson. So find the delta H for the reaction below, which is in bold, given the following reactions and subsequent delta H values. So you have 3 reactions here, okay? 1, 2, and 3. And you have 3 delta H values. There's something for this one to look at as you go through it. And the thing that I looked at first is the hydrochloric acid. All right, so I know I need hydrochloric acid as a product here. I need one of them. The only other place I see hydrochloric acid, and actually it's hydrogen chloride gas, it's not even hydrochloric acid, the solution, because that would be aqueous. So it's hydrogen chloride actually. There's 2 of them here. So I know I need to probably cut this equation in half, but it gets a little ugly because I already have a half O2. All right. So my recommendation for you as you try this one is you could always multiply by a half or multiply by 2 or something like that at the very end. All right. So my recommendation is don't multiply this equation by half yet, because you end up with 1/4 O2 and it just gets really ugly for how you're trying to go about canceling different elements then. Also recognize you need 1/2 H2 and 1/2 Cl2, and you have a Cl2 right here and an H2 right here. Again, you'll eventually need to cut those in half because the coefficients with what I circled are 1, and we want them to be 1/2, but try to wait until the very end for that. So try to organize these, see what equations you need to flip or not flip. Like you definitely know HCl is a product, and here it's a reactant. So we have to do something to that equation. And then we'll see what we end up with at the end. And then you could always multiply by a half or by 2 once you get a simplified version of everything. Okay? So take a second and give it a try, and then we'll go over the solution and then try one more. Okay. So let's take a look at what we need to do here. I'm going to go through the solution really quick on the screen for you, going back and forth between my notes and that blank slide, and we'll go from there. What you definitely want to do is take this equation and flip it, okay? Because you want to get the HCl on the product side. The first equation, what are you going to end up doing there? You're going to end up keeping that as is, actually, okay? And the second equation, the third equation, the last one, you're going to end up keeping that one as is as well, all right? Because we want the hydrogen to be on the reactant side, and it is, because we can't mess with that. We want the HCl on the product side, so we have to flip equation number 2. And in order for everything to cancel out, I need to keep equation number 1 as it is. If I kept equation 3 as is, which I need to because where the hydrogen is, I need to cancel out that COCl2 somehow. And the only way to cancel it out is for it to be a reactant in your first equation. So let's rewrite this by flipping the second equation. All right, so the first equation, COCl2 plus H2O yields CH2Cl2 plus O2. And that was 47.5 kilojoules. The second equation we flipped, so we ended up with H2O plus Cl2 yields 2HCl plus 1/2 O2. If I flip the equation, I need to multiply by -1 for my delta H, so I get -105 kilojoules. My third equation I kept the same, which was CH2Cl2 plus H2 yields COCl2 plus 2H2O. I kept it the same, so my delta H remains the same, and that was -402.5 kilojoules. Okay, let's cancel some stuff out here. So we end up with COCl2 canceling out. Okay, these oxygens here, there's 1 and another half. That gives you 1.5. And if you look at your overall chemical equation, or am I missing one of them here? Oh, I missed it over here. Plus 3/2 O2. Sorry, I forgot about that. So you have 1.5 oxygens here. There it is. Cancels out right there. Forgot to write down from my notes. You have 2 waters right here. They cancel with the 2 waters right here. And it looks like one other thing cancels. The CH2Cl2 cancels here and here. So what are you left with? You're left with Cl2 plus H2 yields 2, HCl. If you notice, that's twice what we need it to be. Let's look at our delta H value. That would be negative 460. You would do 47.5 plus negative 105 plus negative 402.5. You get negative 460. And if you look at the equation that we want to make 1 half H2 plus 1 half Cl2 yields HCl. So it looks like we need to take our equation right here and multiply everything by a half. And that'll give you 1 half Cl2 plus 1 half H2 yields HCl. And multiply negative 460 by 1 half, you get negative 230 kilojoules. All right, so the delta H for that is negative 230 kilojoules. So it's tough because there's three equations here. You got to make sure you include everything. Like I forgot that 3 half O2 because I wrote it underneath because I ran out of room. So once you get the strategy and taken care of here, you kind of could figure out what you need to do based on looking at your overall equation. Here's the last one for today. Give this one a try, and then I'll actually have, if this is an ed puzzle, I'll have the answer pop up when you're done with the solution to double check. This one's not too bad, even though there are 4 equations. Look at your overall chemical reaction. You have HCl plus NaNO2 yields HNO2 plus NaCl. If you just look at what you have going on here, you have HCl as a reactant. The only place you see HCl here is a product. So you automatically know reaction 1, you have to flip. Look at NaNO2 solid. I'm pretty sure that's only found in one location here as well. So if you look for NaNO2 solid, it's going to be right here. Okay? So again, this is a reactant in your overall equation, and it's a product in reaction number 2. So what are you going to have to do there? Do the same thing for the other ones. Here's HNO2 liquid. See if you can find it below, okay, and see if it's on the right spot. And then find NaCl solid. You want it to be a product. Find it in your series of equations, in your reaction mechanism. See if it's on the product side. If it's not, you have to flip it. And then once you flip what you need to, just see if your coefficients cancel out and end up with, for this one, all of your coefficients are going to end up being 1s for your overall chemical reaction that you're looking for. Okay? So take a second, see if you can figure it out. I try to get you started with this a little bit, and then we'll be able to do some more practice problems either in class or for homework. All right? Thanks, guys.